This lesson, we're going to learn how to do curve sketching. Step 1. Given the function f(x), we want to find the first and second differentiation. And then we're going to use factoring to put them into the factor form. Step 2. You want to use the original function f(x) to determine 5 informations. The first one is the domain. Second one, y-intercept and x-intercepts. Here, it's better to use the factor form of f(x) to find it. Third, you want to find the horizontal asymptote and oblique asymptote. This can be found by using the degree of the numerator and the denominator. If the degree of the numerator is equal or less than degree of the denominator, then you are going to have a horizontal asymptote. If the degree of the numerator is higher than degree of the denominator, then you are going to have the oblique asymptote. And remember to check the end behaviors by letting x is approaching to positive and negative infinity. Number 4, you want to find the vertical asymptotes and holes. So they can be found in the restrictions. However, holes are the ones that can be divided into the numerator. Vertical asymptotes are the factors that stay in the denominator. And once again, you have to check with the end behaviors. Number 5, the crossover. Crossover is the point where the function intersects with the horizontal or oblique asymptote. Step 3, we want to use f prime to determine the critical points. So first, let f prime to be 0 to find the critical points, and we draw a number line and put those critical points on with the restrictions to find the increasing and decreasing intervals, and then we can identify our critical points as a maximum or minimum or point inflection. Step 4, we're going to use the second differentiation to determine our point of inflections. Once again, you let f double prime to be 0 to find the point inflection, and then we draw a number line for f double prime, including all the point inflection and the restrictions, and we're going to check the concave up and concave down intervals. Step 5, we're going to combine all the number lines that we have for f prime and f double prime, and sometimes we even use f(x) to determine all the cusp and vertical tangents. Finally, step 6, then we have all the information that we need, then we can sketch the graph. Example 1, given a rational function, we're going to do a curve sketching. Step 1, we're going to find the first and the second differentiation. And step 2, we're going to use the original function to find 5 different informations. Before we find the information, we're supposed to put f(x) into the factor form using factoring. So let's look at the function here. They have an x in common in the denominator. So the first thing is we're going to factor out the x. And then in the bracket, we see a difference of squares. So we are going to factor out the difference of squares to be x plus 1, x minus 1. And now, all the factors in the denominator are the restrictions. So we are going to write x cannot be 0, x plus 1 cannot be 0, x minus 1 cannot be 0. Then we can further simplify it to be x cannot be 0, x cannot be negative 1, and x cannot be 1. So now we can write our domain. Our domain is set of the real numbers. However, x cannot be 0 or positive negative 1. And there is not a way to write domain. You can write the set first, so x on the real, such that x cannot be 0 or positive negative 1. After we found our domain, which is the first information, we're going to move on to the second information, which is the x and y intercept. So, y-intercept, you let x equals to 0 and substitute back into the function, and you are going to get 0 times by 0 plus 1 times by 0 minus 1 in the denominator. And as we know, 0 times by anything will become a 0. And so you're going to end up with 1 divided by 0, which is undefined. So we say this answer is invalid. Therefore, you don't have any y-intercept. The next information we have to find is the x-intercept, which we have to let y equal to 0 to find it. Then you're going to have 0 equals 1 over x times by x plus 1 times by x minus 1. So times by the common denominator on both sides, you're going to get 0 equals to 1. Once again, 0 can never become 1, which is invalid. Therefore, x-intercept, we don't have any. The third information we have to find is the horizontal asymptote and the oblique asymptote. Those two asymptotes can be found by comparing the degree of the numerator and the degree of the denominator, which means it will be easier to use the non-factor form for f(x). The degree of the numerator and denominator can be found by looking at the highest exponent of any term. So look at the numerator now. There's no x. That means we say the degree of the numerator is 0. Next one, in the denominator, the highest exponent that we see is actually a 3. So we say the degree of the denominator is 3. And since the degree of the numerator is less than degree of the denominator, therefore we say horizontal asymptote will be at y equal to 0, and the oblique asymptote will be does not exist. This means the function approaches the horizontal asymptote y equal to 0 from above at the right end, and the function approaches the horizontal asymptote from below on the left end. After we have the horizontal asymptote, then we're supposed to check the end behaviors of the function. In other words, the end behavior of a function describes the trend of the graph if we look to the right end of the x-axis. That means as x is approaching to the positive infinity, what happened to the y value? And to the left end of the x-axis, as x approaching to negative infinity, what happened to the y values? On the right end of the function means when x approaching to positive infinity, we're going to let x to be 100. Substitute into the function to calculate the y. You will see the y value is going to be 0.000001, which is almost 0, but above the 0. So we write 0 plus. On the left end is when x approaching to negative infinity, we're going to let x to be negative 100 to see what happened to the y values, and we substitute this x value into the function to calculate for y. You will see the y value is going to be negative 0.000001, which is also almost 0, but below 0. So we write down 0 minus. Number 4. We need to find the vertical asymptote and holes. Both of them are restrictions and they can be found in the denominator, but the difference between them is holes are the ones that can divide into the numerator, and vertical asymptotes are not the ones that can be divided into the numerator completely. They will stay in the denominator. As you can see from this function f(x), none of the factors in the denominator can be divided into the numerator. Therefore, for this function, we do not have any holes. Now let's find our vertical asymptote. Vertical asymptote are all the restrictions that stay in the denominator. So the first one is x cannot be 0. So therefore, we write on vertical asymptote x equals to 0. The second one is x plus 1 cannot be 0. That means x cannot be negative 1. Therefore, the vertical asymptote will be x equals negative 1. The next one is x minus 1 cannot be 0. That means x cannot be 1. That means vertical asymptote will be at x equals 1. And then for all the vertical asymptotes that we have, we also need to check the end behaviors. For each of the vertical asymptote, we have to check the right-hand side limit and left-hand side limit along this vertical asymptote, because we need to find out how does the function f(x) approach the vertical asymptote. When the function is approaching to the vertical asymptote at x equal to 0 from the right, that means we let x to be 0.001, substitute into the function f(x) to find the y value, which is approximately at negative 1,000, and we know the limit is going to be negative infinity. So next one, when the function is approaching to the vertical asymptote x equal to 0 from the left, we let x to be negative 0.001, and the y value is approximately at 1,000, so we know the function is approaching positive infinity. Next, when the function is approaching to the vertical asymptote at x equals negative 1, from the right, this time, the x value will become negative 0.999, which is on the right-hand side of the negative 1, but very close to negative 1. You see the y value is approximately at 500, so once again, it's positive infinity. And find the left-hand side of the vertical asymptote means -1 on the left, and the x value will be -1.001, which means on the left-hand side of the -1, but very close to x equals -1. Then we find the y value is -499, which is -infinity. Similarly, you can do for the vertical asymptote by x equals to 1. Then your x value will be 1.001, y value will be 499, which is positive infinity. And from the left-hand side of the vertical asymptote, x approaching to 1 from the left, which is x equals to 0.999, your y value will be -500. That will be -infinity. Number 5, crossover. Crossover means the point of intersection where fx intersect with horizontal or the oblique asymptote. In this function here, we do not have oblique asymptote, so we're going to find where fx intersect with a horizontal asymptote. So we know fx equals 1 over x cubed minus x, and we also know horizontal asymptote is y equal to 0. At the point of intersection, they do share the same x value and y value, so we're going to equate them together to find where the x value is. So 1 over x cubed minus x equals to 0, multiplying by the common denominator on both sides, you're going to get 1 equals to 0, which is invalid. Therefore, we know there is no crossover in this question. Step 3, we're going to use our f prime to find the critical points. The critical points can be a maximum, minimum, or a point of inflection. So first, we're going to factor f prime. So as you can see, there is a common x in the denominator. After we factor out the x, you can see a difference of squares. So we can factor down further and then apply the power 2 to every single factor. And now we have a simplified factor form. Next, we're going to let f prime to be 0 to find the critical points. Then we have 0 equals -3x squared minus 1 over the entire denominator. And at this time, we're going to write down restrictions. X cannot be 0, -1, and 1. And because 0 times by anything, it will be 0. Therefore, we're left with 3x squared minus 1 equals 0. That's isolated for x squared, so 3x squared equals 1, divided by 3 on both sides, x squared equals 1 over 3. In order to get rid of the square, we have to take the square root, so x equals to positive -1 over root 3, which is approximately positive -0.577. Now we have the critical points, we have the restrictions, that's put on the number line. And remember, all the restrictions are the empty dots because we don't need to identify them. And all the critical points are the solid dots. Those are the points that we have to identify as a maximum, minimum, or point of inflection. And then we substitute the values into f prime to check the positive, negative sign. You'll see negative, negative, positive, positive, negative, and negative. So this means at x equals -1 over root 3. On the left-hand side is negative, means decreasing. On the right-hand side is positive, means increasing. So we have a local minimum here. And at x equals 1 over root 3, on the left-hand side is positive, means increasing. On the right-hand side is negative, means decreasing. So we see there is a maximum. Now that we have the x value, we have to find the y values. We're going to substitute those two x values back into the function fx to find the y. So when x equals -1 over square root of 3, we will get the y value is 3 root 3 over 2, which can be approximated to -0.58 and 2.6. And same thing, when x equals 1 over square root of 3, then y value will be -3 root 3 over 2, which can be approximated to 0.58 and -2.6. Step 4, we are going to use the second differentiation to find out the point inflections and the concavities of the function fx. So first thing is we try to factor f double prime into the factor form. So the numerator cannot be factored, so we just factor out the denominator to be x cubed, x minus 1 to the power 3, x plus 1 to the power 3. This will help us to find the restriction easily. Next, we're going to let f double prime equal to 0 to find out the point inflections. And the first thing we write down will be the restrictions, which is from the denominator. X cannot be 0, 1, and -1. Next, since we know 0 times by anything will become 0, therefore we're going to have 0 equals to 2 times by 6x to the power 4 minus 3x squared plus 1. And we know 2 can never be 0, so we divide it by 2 on both sides. You get 6x to the power 4 minus 3x squared plus 1. And how do I solve for x here? As you can see here, this is quadratic in disguise, so we can use the quadratic formula to find it. So x squared will be negative b plus or minus square root of b squared minus 4ac divided by 2a. And as you can see from this square root, 9 minus 24 will become a negative 15, which is an imaginary root. Therefore, we say this is invalid, therefore there is no point of inflection. Now, at this time, we're supposed to create a number line for y double prime and put all the points inflections and restrictions on the line. But since we don't have any points inflection here, we only need to put on the restrictions on the number line. Because they are restrictions, so we need to use empty dots on -1, 0, and 1. Once again, you have to substitute different x values from each interval into f double prime to check the positive negative sign. Then you're going to have positive, negative, positive, negative. Unlike the number line for the first differentiation, which is used to classify the critical points, here we are not classifying the point inflections, but we are only here to find out the concavity intervals of the function f(x). Step 5, we're going to combine the number lines for f prime and f double prime to check the location for the cusp and vertical tangent if they exist on the graph. First, let's write down the number line again for f prime and f double prime. And according to each critical point and restrictions, we are going to cut them into different regions. Next, since I cut this one interval into 2, so I'm going to rewrite a positive sign here and negative sign here. Now let's identify the shape of each interval of the function. So first of all, we know y double prime means the concavity. So whenever it's negative, it means concave down. When it's positive, it means concave up. So I can see this. Concave down, concave up, concave up, concave down, and concave up. Next, the first differentiation tells me the increasing or decreasing interval. Negative means decreasing and positive means increasing. So let's take a look at our concavities. So in this interval, it's decreasing. So that means I only pick this part because that's decreasing. And the next one is decreasing as well. So I'm going to pick this part because that's decreasing. And the next one is increasing, so I'm going to pick this one because that's increasing. And the next interval here is positive, that means it's also increasing again. So I'm going to pick this side because that's increasing. Next interval, this is decreasing interval, so we have to pick this side of the U shape because that's decreasing. And the last one, this is decreasing as well. That means we have to pick the decreasing interval, which is on the left-hand side of the U shape. Now let's draw the shape inside the interval. So it's going to be this way, that way, this way, that way, this one, and that one. Finally, we can identify the location of the cos and the vertical tangents based on the shape that we have already. So at the cos and vertical tangent, the differentiation will not exist, which is the restrictions. However, if the restrictions was coming from the vertical asymptote, then it will not be the cusp and it will not be the vertical tangent. And we know from this function, the vertical asymptote happens at x equals -1, x equals 0, and x equals 1. Therefore, we can say there is no cusp and vertical tangent for this function. And based on the graph, we can clearly see there is a minimum at x equals to -1/√3, and there is a maximum at x equals to 1/√3. Step 6. Now we're going to use all the information that we have to construct the graph f(x). Before we put any information on the graph, we have to label x and y axis, and we have to define our scales. Because we need to have a point such like 0.58 and 2.6, that means I am going to use 2 squares to represent 1 unit. After we have the label, we have the scales. Then I follow the order of f and f prime and f double prime to put all the information on the graph. First, let's put x and y intercepts on. Since we don't have any, therefore, there's no x-intercept, there's no y-intercept. Next, I put all the asymptotes on, and make sure you use dotted line because asymptote doesn't exist, and you put the equation of the asymptote at the end of the asymptote. Next, we're going to put the location of the crossover on. Since we don't have any crossover, so we don't need to put that point on. Now we are ready to put the end behaviors on. When x approaching to positive infinity, y is approaching to 0, positive. That means the function approaches the horizontal asymptote from above on the right end. And we know when x approaching to negative infinity, y is approaching to 0 from below. That means the function approaches the horizontal asymptote from below on the left end. Now for the vertical asymptote, when x approaches to 0 from the right, y is approaching to negative infinity. That means on the right-hand side of the 0, y is going down. That means function is going down. And 0 from the left, y is approaching to positive infinity. That means on the left-hand side of the 0, the function is approaching to positive infinity. And when x approaching negative 1 from the right, y is approaching to positive infinity. That means going up at the right-hand side of x equals negative 1. And when x approaching negative 1 from the left, y is approaching to negative infinity. That means on the left-hand side of the negative 1, the function is going down. Last one, when x approaches to 1 on the right, y is approaching to positive infinity. That means on the right-hand side of the vertical asymptote x equals to 1, the function is going up. And when x approaches to 1 from the left, y value is going to negative infinity. That means the function is going down on the left-hand side of x equals to 1. Let's move on to the information from the first differentiation. We know there is a local minimum at negative 0.58 and 2.6. So there's a point and there's a minimum. So draw like a minimum. And next one, 0.58 and negative 2.6 will be a local maximum. So draw the point and draw a little maximum right there. Normally at this time, we're supposed to move to the second differentiation to put all the points of inflection down. But since we don't have any, so we can skip that step. Moreover, because we find out there's no cusp and vertical tangent, therefore, we're going to skip that step as well. Finally, let's use all the information that we have on the graph to generate our sketch. After we generate a sketch, we can verify it with our number line. So from negative infinity to negative 1, the graph is supposed to have a shape like this. That's why we have this one. And from negative 1 to negative 0.58, the graph is supposed to going down. So we have this part. And next one going up. That's why we have this one. And going up, so this region here. And going down, that's this region here. And the last region is going to be like half of the U shape. There it is. Therefore, we generate a very good, accurate graph.